including people who joined us from the afternoon session, we had an issue with our system, fixed it up. Right, so I'm going to quickly run through you with a very small short presentation on what's new in Sim5X and HSS. Some of the slides are basically GUI changes, so I'm not going to spend much of my time on those changes. What I'm going to do basically is to spend more time on the new features, the new more exciting features of SolidCAM 5-axis. Right, the first was some geometry changes in the GUI, where we moved the boundary curves from another place to geometry because we felt that was more logical. There were also changes to the levels page, where we introduced an advanced parameter and moved some of the regular parameters into the advanced function, which are not used mainly they are not mostly used, and they're used only when certain things need to be controlled. Right. Also in the Toolpath parameter page, we added a modify function, moved some of the parameters into modify, made it much more easier and simpler. Basically, we modified our GUI to make it much more easier to work with in 2015. Right, we run with our first new feature, and that is feed control. Feed control basically is a very interesting addition to HSS and 5-axis, where it enables users to reduce or increase cutting feed inside or outside a selected volume of material. Now, when I say volume of material, it means that these two things can be defined, or rather the feed control can be defined using two different methods. One is selecting the area itself of the geometry, or making a new geometry and defining that as a new volume for feed reduction. Right, so what we're going to do now is simply run into the software. I have a part out here, okay, and simple part, and I've created an HSS operation. So let me edit this operation. And if I go into the tool, we have a feed control zone. I'm going to go switch off that. And the data, I've given the cutting feed as 2000 mm per minute. So let me hit save and calculate and generate the toolpath. This should take about a few seconds. Okay, that's done. Now if I run my tool in my host CAD simulation, you can see that the feed is constant. It's pretty constant. Even if it goes into the corner, it's still going at 2000 mm per minute. Generally, the trend among machinists is to drop the feed rate when it hits a corner. Especially when you're doing conventional kind of machining, you need to drop down the feed rates. So what we're going to do now is we're going to introduce the feed control function. So I'll switch on the feed control, and we will use the first method, and that method is to use the geometry faces itself. Rather than creating something new, we are going to use the geometry face itself. So I'm going to select new, and I will pick all these fillets out here. Okay, picking this fillet. So we picked up about 7 different or 8 different geometries of the fillet. I'll select that as OK. And I will define an offset of about 5 mm. Now when I say an offset, basically it will offset out the entire geometry by 5 mm and allow me to reduce the feed within that offsetted geometry. Or I could say just give an offset of about 0.5 mm or even 1 mm. Okay? And within that volume, I will drop the feed rate. I'll drop the feed rate by about 50%. Okay, great. Let me recalculate this. All right, that's done. Now let's go back again to our host CAD simulation. It's 2000 mm per minute, but you can see the moment it comes into this area, SolidCAM drops down the feed to 50% of the cutting feed rate. That's about 1,000 millimeter. So it travels over this area by 1,000 and then increases again to 2,000 before it comes to hit this area out here. The moment it is into this area, you can see that it has dropped down again to 1,000 millimeter per minute. So this is one way of handling the feed control. Let's look at another way. So I'm going to make a copy of this operation. Make a copy and paste it. Okay. Now what I have also done in this part is basically modeled or created few solid geometries. Okay, these are 4 extruded geometries that I've created. I'm going to switch them on. Okay, rather than defining the faces of the part itself, what I'm going to do is, because here I can control even at what height the feed rate can change. For example, I could have one of these extruded geometries starting only from half of this and going below. So I will have 100% feed rate on the top, and the moment it goes down, it will start reducing in the corners. So the volume makes much more sense when you would like to have differential feed rates at different levels on the model. Okay, so let me edit this, go to the feed control, and I'll say new. And I'm going to pick the color from this and find all the faces of that particular volume. Say OK. I don't want to provide any offset to this, so I'm going to make that as 0 and hit save and calculate. Okay. That is done. Let me switch off the volume so that you can see how the tool would look when it moves into the area. So you can see that we still have the outline of that geometry that we created. So we can check once the tool gets into that area, how is it behaving. Oops, sorry. That's pretty fast. So you can still see it's at 1,000. It's still 1,000, and it's gone to this area again down to 1,000. So this function is very important, especially you have when you have tools with out of holder length beyond beyond the L/D ratio of about 5 or 6. And when you are going down on the corners, you would like to drop down the feed rate so that it doesn't vibrate in those areas. So this feature is pretty important, and it is available to us both in HSS as well as in 5-axis. All right, let's move back to our presentation. Another very important thing that we added was to synchronize the cutting points of the toolpath points on the toolpath. You can look at the figure on the right side. The first one is the point distribution without using the synchronized point option on, and the second is with synchronization on. We will see this now in the software itself. It's pretty important. And what is the benefit of this? The benefit of this is you get a much better surface quality when you're cutting complex surfaces, because the toolpath point distribution on the surface is uniform all throughout the surface. So you get a much better surface quality than what you were getting before. Right, let's again open another file, and I can show you the example on how this behaves. Right, I have a part here, and I'm more interested in cutting on the surface. So what I've created here is a toolpath using parallel to curve option. Where I have the geometry. I have a 10 ball nose tool, and in the toolpath I'm going to switch off the distance option and a step over of 3, and let's calculate the toolpath. So we will see 3 scenarios, one without the point distribution, one with the point distribution but without the synchronization on, and the last one is including all the 3 options on. So let me run a machine simulation because I can show you the point distribution much better there. Okay, there we are. That's the toolpath, and that's the part. Let me hide the part for a moment and switch on the synchronization, switch on the point display. You can look at the points on how they are distributed. You can see that some of the points are distributed coarsely out here, and again they are densely distributed. Again there's a coarse distribution, and again there's a dense distribution. So what this is probably going to do is it's probably going to give you a better surface finish in this area, a better surface finish in this area, but here you will see that the point or the quality of surface is going to be not as good as the areas where you have got a much denser point distribution. So what we do is we basically switch on the distance option, where we get the distance between 2 points. It's going to keep is about 0.5. Whether it hits the tolerance or not, we are going to have a point at every 0.5 millimeter on the toolpath. Let's calculate this. Okay. Let's run again the machine simulation and see how the toolpath looks like. Right, we have the toolpath. Okay, and we switch on the point distribution. You can see that if you look from top, you can see again dense distribution of points over here. Okay, and it's again coarse, dense in some pockets, and so on. So basically it has not done a proper distribution or synchronization of points. So what we will do now is, what we can do now is actually change it to 1 and calculate and show you, because 0.5 was too close to see any difference. Okay, let's go back to the simulation. Right, you can see that. You can see how dense the point distribution again is here. It's dense here, and then it's okay on the other side. What we are now going to do is, the same toolpath, we are going to switch on the synchronize points option. You can see that the synchronize points option comes up only when the distance is selected. When you select the distance checkbox, only then you see the synchronize point option on. Let me hit the save and calculate button. Okay, let me run the simulation now into machine simulation again. Okay, we have same toolpath. I'm going to switch on my point distribution, and you can see how the point distribution changed when I checked up the synchronized point option on. The point distribution has become extremely equal in every segment of the toolpath. So we are actually not going to have issues with surface quality where you have got much better surface finish in some areas and coarse surface finish, or the surface finish is not as good as that surface in some other area. The synchronized point option basically will distribute the points equally, it will distribute the point equally on every segment of the toolpath, so that you have one point. If I go here, back to the, and if I zoom into this area, you can see that the point on the first segment and the point on the second segment is on the same level, is in the same line. It's not going up and down, or it is not changing its position in the second, third, fourth, and fifth segment of the toolpath. So it is very important to note this very extremely important feature, that when you use the synchronization of points, you get much better surface quality because the distribution of points is equalized over the entire toolpath. Right. Let's go to the next option. We again did some, what we can say, cosmetic changes to it, because we wanted to be more logical in renaming of some of the strategies. When you're using Gouge check, we moved some of the options of another Gouge check parameter into retract tool, so that we got everything in one logical order and renamed them in such a way that it is much more easier to understand. We also have some nice new feature called smooth retracts. You can see over on the picture out here that when you use this retract along tool axis option, you get an additional option to smoothen the retracts. What it basically does is it tries to make a tangential transition from the toolpath that is gouging to the toolpath that is safe. Rather than giving you sudden axis change or sudden change in Z, it makes a very smooth transition between this toolpath or this area where you have gouges. So this is a pretty nice option when you are trying to use the smooth retract, or rather the retract along tool axis option. I mean, you get the advanced button, and in that you have the smooth retracts. We also made some changes to the Gouge check clearance data page. We removed a redundant option to keep only 3 logical options in it. Okay. We have got another nice function inside the roughing and more, where we use only, we have this new feature for trim only full contours. What it basically does is, rather than trimming off toolpath that are just slightly outside the stock, rather than being exact in trimming off the contours, because that can cause a lot of air cuts. You'll see a lot of retracts because some portion of the toolpath was not inside the stock, so it was removed. Rather than doing it, we only now remove a complete contour if it's not inside the stock. Even if some portion of that is in the stock, we keep that toolpath, so that there are no jumps. The cutting is much smoother. Right. Some more options in tool axis control. When you're using the lines, tilted through lines option, we have got a new option now, which is always closest to the surface, in which the software will use the tilt lines that are closest to the surface. You don't need no more now to define the snap distance, and then it comes up with a message saying that it did not find the tool axis, or rather the tilt lines within the snap distance, and then you need to keep playing with the snap distance. Instead of that, we just say always use the lines that are closest to the surface, and only those lines will be used to define the tilt axis of the tool. Another nice and interesting option in Sim5X. We have got another new tool axis control option, and that is tilted through a contact point, or tilted relative to a contact point. With this option, basically, rather than the software trying to tilt relative to the cutting direction, we now tilt the tool relative to the contact point of the tool on the surface. This gives a much better and a much predictable tilt rather than tool trying to dance on the surface, because it gets too many different tilt angles. So the tilting is much more smoother when you use the tilted relative to contact point option. Right, then we come to our most important release in 2015, and that is MultiAxis Roughing. MultiAxis Roughing basically is an operation for roughing of pockets that would probably need multiple setups if it was done in 3-axis. So you have a twisted pocket and you would like to rough that. It would have required a great deal of effort to machine it. With the new option of multi-axis roughing, this is much more easier. What it basically does is it creates multi-axis toolpath that can be used to rough out pocket-shaped geometries. And how it is done? The user simply has to specify the floor and wall geometries, and the system creates a toolpath automatically with ramping. Or if you have an option not to ramp, even ramping, you have got different options. What is more interesting in multi-axis roughing is we have got a very nice feature called as an adaptive roughing, which mimics the constant step over principle of a 5-axis. So quickly, let's get into our software without wasting time and see how this works. All right, so we have a nice twisted part, and we would now like to rough out these pockets using the multi-axis roughing principle. Okay, just for your knowledge, what I've done is there's a stock that's already created so that it becomes much easier for me to show you the simulation, and I also have a holding fixture below to hold the part. Okay, great. So we don't need to see these. We are more interested only in the other part. Right. What we are going to do now is we will add multi-axis operation. In fact, we are going to add two different operations in this. Maybe an eye machining 3D, and then we will add the swarfing for the side and also the multi-axis roughing. Okay, so let me switch on the stock because I will need this, or rather I would need the points for my cutting. Okay, so let's add 3D eye machining just to rough out the external one, and the geometry that I'm going to use is model, because what I want to do is I don't want the tool to enter into these pockets. So it's going to stop on the outside. I've created a surface, so it's going to stop on the outside. Let me pick the tool. I'm going to use a 16mm end mill. Okay, and we're going to use the holder clearance. Lower level is out here, it's -185. I know it's not going to go completely to the end. Level 6, 0.5mm is my step over. Okay, great. So let me save this. 50 microns and calculate. This would take about a minute, so we'll have to be a bit patient here. Okay, we've done that. Let's look at how the simulation looks like. Let's run the solid verify. That's the stock. Let's quickly run. Now, you can just go ahead. All right, so we have roughed out, but I did not enter into that area. What I also need to do is to just finish the top so that it becomes much more easier. So let me add a 3D HSM toolpath, linear machining. Okay, we're going to use 12 ball nose, and the constraint boundary is this one, and step over, let's say, it's 1 millimeter for machining. Okay, link bidirectional, retracts minimum. Save and calculate. Okay, don't worry about the rebuild, but we are more concerned about the toolpath. Right, so we have finished the top. We're now ready for machining the inside using the new function, MultiAxis Roughing. Okay, great. Let me add MultiAxis Roughing. Okay, quickly I'll explain you the philosophy of the multi-axis roughing. In multi-axis roughing, the tool is always going to be normal to my floor. Irrespective of how your wall is, it's always going to be normal to the floor, and it will retract, enter, and also machine the part normal to the floor always. Okay. Let's go to the geometry. We'll use the offset strategy, floor. So we need to pick the floor surface because we're using the offset from floor strategy. So I'm going to pick these 4 surfaces. These are my floor surfaces. And then I have an option to pick the wall surfaces. When I want to pick the wall surfaces, what I basically can do is I can manually pick the walls. If there are 1 or 2 or 3 or 4, I can do that manually. But in this case, there are many. So what I'm going to do is I'm going to go to New, and instead of saying just 1, 2, 3, 4, let me again pick the color and pick everything, including the floor surface, as my wall surface. What I've done basically is I've just picked everything as my wall. The software is pretty intelligent in understanding what it has to do. So it does segregate between what it considers as floor and what it considers as wall, because I've already indicated to it what my wall floor surfaces look like. So it does its own segregation and moving around. Like to keep about 0.5 millimeter on the floor and also on the wall. Let me use a 10 millimeter bullnose, corner radius 2, levels. I just want to change the entry and exit distance to 5. Boundary, I'm going to define automatic. Let the software create its own boundary. Toolpath parameters, since I'm doing roughing, I would like to create the toolpath with 50 microns tolerance. Step down, because I want to show you quickly, so I'm going to use a bigger step down and a bigger side step. Okay. Of course, I have an option to define the depth as either a step down, or I could define how many slices I need in it. So I have option to work with both step down as well as number of slices. Sorting, I'm going to do zigzag machining, and the machining is going to be either by levels or by regions. So you can use either of them. Smoothing, you can smooth the corners, you can smooth the final contour, you can put a radius at the end, at the sharp corners. Smoothen the links, you can have much better linking between each segment of the toolpath. And if you're using a much bigger side step, you could also use remove corner pegs. The small material that remains when your step over is large, much larger than half of the tool diameter. That's when you start getting this corner pips, which are triangular shaped material that will remain. So this fellow, or this particular option, will add an extra toolpath or an extra motion into that area to remove the corner pips. But since we are not using more than half of the tool diameter, I'm not going to use this option. In the link, we have got the ramp angle, which I'm going to keep it at 5, and we will use helical as our ramp type. In the approach and retract, the first entry I would like to use ramp. The last exit I do not need any kind of ramp, just as to leave out. Within group, direct, but I would like to use ramp. Retract, rapid distance, or between groups, again I would like to use ramp. Between slices, I would like it to retract to the rapid distance, use the ramp. Between regions, to rapid distance, use the ramp. So this is all that I need to define in the entire process. Let me save it and calculate. This would take about 35-40 seconds for the calculation to finish. Okay, the calculation is done, and what we now need to do is to look how the toolpath looks like. Let's first switch on the entire toolpath, and this is how it looks like. We've got a nice ramping in, and you can look at how the links look like. Right, so let's run the machine simulation to see how this toolpath would cut on the machine. Okay, that's the machine. Going to switch on the part and also switch on the machine so that you can look how the machine looks like. It's a DMU 680 evolution machine. Okay, let's switch off the toolpath and let's look how the machine would run. It's full 5-axis roughing. So it's a pretty nice option in which you could cut complex pockets which need, for example, they have undercuts and you would like to do roughing. Generally what we do is we do 3-axis roughing and then we tilt the part and do the undercut portion. With this option you could run the entire machining. You could run the entire machining in one go using the multi-axis roughing option. Right. So let's look at another option inside multi-axis roughing, which mimics, like I said, it mimics the, I would say it looks very similar to the constant step-over principle toolpaths, which also uses, by the way, the same principle here. So let's copy this toolpath and paste it below. Let me edit. And let's go to geometry. Now the strategy, instead of offset, I'm going to use adaptive. Okay, I won't change any geometry or anything. Tool also won't change. However, in the toolpath parameters, you can see that the other parameters now open up. We have got the maximum step over and the desired step over. So it is going to play between these two step overs to try and give you some kind of a constant cutting on the material of the tool. Okay, so instead of going with a step down of 5 millimeters, what I'm going to do is I'm going to use just one slice, because we would like to see how the toolpath looks like in adaptive inside SolidCAM. We're not going to use the step down, but we're going to use the number of slices. Okay. There's no smoothing. You can see that the smoothing has already disappeared because we are using an adaptive principle. All right, everything else is just the same. We are not going to change anything in this. Let's save. Okay. Let's go geometry and let's change certain areas here. To not use RAM, and then let's come back to the adaptive. Okay, that should fix it up. Let's save. About our tolerance. Okay, great. Let's hit save and calculate. Again, this would take about 30-40 seconds to calculate, but the toolpath will be worth looking. All right, we have done the calculation. Let's look at how the toolpath looks like. Oh, okay, sorry, because it's not getting any option on there. Let's make this a 0. Let's run the calculation. That's done. Let's run and look at how the toolpath looks like. You can see how the toolpath looks. This is very similar to the constant cutting angle or the constant principle toolpath. So if you run this in simulation, the machine simulation, it's even more interesting because the way the machine behaves. Okay, let's open up and let's look at how the toolpath will run. That's how toolpath run. The advantage here is you can actually use the full cutting length of the tool and go complete depth in one go. By keeping the step O constant, you can ensure a near constant load when you're cutting the toolpath. You can see that's pretty nice. It looks very nice when it's cutting. The way it handles the corners. All right, so let's stop this. Let's quickly run through our next features. Basically, we've got some other interesting features. Again, some changes in the multi-blade GUI. We moved some level section from another place to where it actually belongs in clearance. We added minimum and maximum machine angle limits and tool axis control with reference to 2014, of course. And then we have got the function to introduce plunge arcs. So let me again open one of the parts and show you what we mean by plunge arcs. So I'm going to open one of the impellers. All right, so I've got several operations in this, but what I'm more interested is in showing up the finishing operations where we introduce this option called plunge arcs. So in the link between layers, I have got an option to put plunge arcs. So let me show you without plunge arcs how the toolpath would look like, and with plunge arcs how the toolpath would look like. You can also observe another thing in the multi-blade engine that's being released with 2015 SolidCAM is that the toolpath calculation is slightly faster than 2014. That's because we've done a lot of changes inside the multi-blade engine itself. Okay, that's done. This is how a regular toolpath would look like. And what we have to see out here is the entry, because that's where we have introduced that option. So what I'm going to do is just change to number of 12 and go to the link and change it to plunge arc. So you've got the arc sweep diameter and the angle. Okay, let's calculate this toolpath. Because earlier, why we introduced this parameter was that the tool was directly going on the surface straight away. There was no way to control it. Now we have got a much better control. And you can see what has happened out here. So we have got a nice arc out here that moves into the machining area. Right, so this was the next option of our enhancements in 2015. Right, let's move to the next one. There are a few of them. Again, there was some GUI improvements in multi-blade. In the previous one was in roughing itself. And then we renamed some because there was no point in keeping them as roughing and more because it's already roughing, so we changed it to more logical names, stock and transformation. Okay, we also have some improvements in our port toolpaths. If I open one of the port, what this basically does is it gives you an option to smoothen out the tilt motions. How is it done? So it's done using this option out here, minimize tilting. The moment I use this option of minimize tilting, it reduces the tilting motions on the machine. It doesn't eliminate them completely because it's not possible that they can be eliminated, otherwise we'll not be able to machine the port, but it completely reduces them to a great extent so you can get a much smoother motions on the machine. Of course, on this part they won't be visible heavily on the screen, but on the machine you can see a marked difference in the way it behaves or in the way the tilt happens. While that is going on, let's run through our other announcements so that I can only show you the files. We've got much more better feed control now in SWARF, where we can adjust the feed rates on edges and also when it is doing the fanning operation. Moving from one angle to the other, we can adjust our feed rates by providing minimum and maximum feed rate values. It uses between these values so that one, it doesn't damage your edge, and the other one, when it's doing fanning, generally on machines with RTCP, the feed rate goes up drastically high when it moves from one area to the other where the point contact is still the same. So there we cut down on the feed rates so that the movement is smoother and is with a much lower feed rate. The direction of surface selection now in SWARF is now it's possible to use surface normal rather than indicating left, right, or outside, inside, or automatic. You can now, or rather the software will now determine which side of the surface it has to machine by just using the surface normal. There are some nice extensions, automatic, align to edges and start with an angle. These are extensions available inside SWARF where we can extend the toolpath basically from the start and end point. Degouging strategy. We have got some nice degouging strategies now where you can completely degouge the tool, or you could balance between how much the tool is allowed to gouge and how much allowance you would like to leave on the SWARF surface. A new function inside SWARF now allows you to rotate and translate your SWARF toolpath. It was a big user request from a long time, especially our multi-blade customers who wanted to just do a SWARF cutting of one of the blade and then rotate it. And in multi-axis drilling, we have got the use cycle option. Earlier, it was always by default, the cycles were being generated. Some machines in RTCP mode cannot use cycles. In such cases, we need to break these cycles into linear moves. So this is done simply by unchecking the box of use cycle, and you can directly get linear movements. Okay, let's see how the toolpath has progressed. It's done. Let's run the machine simulation because it will be more visible out in the machine simulation. Let's go to the front view. Okay, and let's run the simulation. You can see that my head movements are kept to bare minimum. Otherwise, it would generally dance around. And once it is inside where it really needs to move, it starts moving. Even on the side, very few movements. So this function basically cuts down the tilting motions on the tool, on the head, thereby giving you a much smoother motion when it's doing the actual cutting. Okay, let's look quickly at the SWARF because that was a very important subject for our announcement inside SolidCAM. I have an impeller out here, and what we are going to do is we are actually machining these surfaces using the SWARF function. So when you go into SWARF and you go into roughing and more, you have got an option to rotate and translate. So I can use the rotate and translate option, number of steps, start angle. Okay, and let's calculate this. Earlier, my customer used to complain that they have got 6 or 7 different blades, and every time they need to create a separate toolpath for the blade for swarfing it, because they would like to finish the impeller, or they would like to finish it with swarfing option and not with single passes. Okay, that's done. So we have a toolpath. Okay. Whatever. What is it? Strange, it went off. Sorry for this interruption. Again, there was some issue. So we have got the swarfing toolpath now. So if I run the simulation, that's blade number 1. And then it uses a transformation, goes to the second blade. Again, the transformation, third blade, and the fourth blade. So this is a new nice announcement. Again, it was driven by the request from the customer that they would like to see the SWARF toolpath with rotation and translation. All right, we'll see one more announcement that we just talked about, and that was the Gouge check. So we have a surface which is curved. Sometimes customers just want that we will use swarfing to cut such surface. So let me edit this toolpath. So we have this Gouge check. Let's generate the toolpath without the Gouge check option and see how it works. You can see there the tool is already gouged. Now this is perfectly all right because we have selected the surface. What the swarfing engine does basically is takes the upper curve and the lower curve, creates a drive surface, and then machines that surface. So it's basically only taking the upper edge and the lower edge and the surface. But if it's gouging, then we have an option to degouge it. So we'll degouge that and we'll calculate. Right, that is done. let's run again. And you can see that the software now has pushed the tool out. However, we do have a problem now, because again, some of the customers do come up with this option. They say, hey, look, there's a lot of material remaining here and here. We don't mind it gouging more inside, but we would like to remove excess material. In such cases, we have an option either to balance it. That means it will balance between gouge and it will balance between the amount of material remaining. And then you have an option to balance it between how much you would like to gouge and how much excess material is allowed to remain. So if I say my excess material allowed to remain is about 2 millimeters and calculate it, so it will create a toolpath in such a way that it is allowed to gouge by that amount, and it's also allowed to keep 2 millimeter material. So it tries to balance the entire cutting. In order to understand that better, let's switch off the solid and switch on the surface so that it's easier to see the gouge. You can see that it's gouged inside. Why? Because it's trying to keep that 2 millimeter of material excess. So it's trying to create a balance between how much it can gouge and how much excess material it can keep. So by playing with these parameters, the customers can actually make a nice swarfing toolpath even on surfaces like that, where they can completely degouge it, or they could give an allowance to gouge and also for the material to remain. So it does a balancing act between how much is needed to be gouged inside and how much material still needs to be kept out. Okay, basically we have come to the end of our presentation of the enhancements in 2015. If there are questions, you could tell Sydney the questions, and then I'll be more than glad to answer it. Yes, there was a small disruption. It's been sorted out. Sydney, I'll leave the screen to you, and you could take the questions. You could either chat or put it in the chat area so that I can answer the questions, because for some reason I'm not able to hear the audience.
Okay. Amo, thank you very much. There are no questions. Everyone have a great weekend, and we'll see you on our next webinar.